Brilliant, welcome everyone. We're going to dive from talking about serverless. Jan did an amazing job there talking about serverless, where you really don't have to think at all about the underlying machines. And now we're going to go completely the opposite direction and really dive into some things that are happening in the kernel and on our servers. My name's Liz Rice. I work for a company called Isovalent, which is now part of Cisco. We recently got acquired by Cisco. And we have been very involved in this technology called eBPF right since the get-go. And that's what I'm going to talk about today and about why I'm so excited about eBPF. Also, is there anybody here who is using Cilium at all? Cilium networking project. I see a few hands going up. OK, brilliant. So Cilium is best known as a networking solution for Kubernetes. It's very much based on eBPF, and I'll talk about a couple of Cilium projects in this talk this morning. And yeah, let's dive in. eBPF, so actually no, before I tell you what eBPF is, a little bit about me. I've been very involved in the CNCF, the Cloud Native Computing Foundation, for quite a long time. That's the organization that owns Kubernetes. It owns Cilium now. I'm also an AWS container hero, and I'm very much sort of have an engineering background. I've written a few books, and I think we have a few copies of Learning eBPF that are going to be part of the raffle at the end of today. So if you get one of those prizes, then I'll be more than happy to sign it for you. So this eBPF thing that I've been mentioning sounds like an acronym, and it used to stand for Extended Berkeley Packet Filter, but you can forget that, because really it does so much more than filtering packets that this is now pretty much misleading. So we just think of it as a standalone term, eBPF, and it allows us to dynamically program the way the kernel of a machine is working. So when I talk about the kernel, let's make sure we're all on the same page about that. Most of the time, if we're application developers, we write code that runs in user space. But unbeknown to us, our application code has to make calls to the kernel, which is the privileged part of the operating system, anytime it wants to do anything that touches hardware. So if you want to send or receive a network message, or you want to access a file or write something to the screen, all of these things involve hardware, and the kernel has to do that on behalf of your applications. The kernel's also involved in coordinating multiple different applications that might be running at the same time, and looking after privileges and permissions, things like whether or not you're allowed, or whether a given application is allowed to access a file, for example. So our applications are making these system calls to ask the kernel for help all the time. And with eBPF, we can attach eBPF programs to events that happen in the kernel, and then we can either observe all these calls that have been made and other activity that's happening in the kernel. And we can even influence the results of these events. We can influence the way the kernel behaves using eBPF. So I want to show a quick Hello World demo to make this clear. Hopefully this is just about big enough that you can see. The eBPF code that I'm actually going to run here, all it does is a line of trace, and let's make this say Hello Istanbul, to customize it. So really it does nothing except emit a line of trace. But I'm going to attach this eBPF program to a system call called execve. And execve is used to start a new executable. So every time you run an executable on the machine, it's calling this system call. So I'm going to attach my eBPF program to that system call. So if that is saved. So if I run this, and nothing much is going to happen until I cause that execve system call to run. And whenever it does, so if I run in a different terminal window on the same machine, it generates the line of trace. And doesn't matter what I run here, it will trigger that executable, that eBPF program to run. So we can load programs into the kernel and trigger them through these events. That didn't do anything particularly useful, but it did have information available, things like what the process ID was, what the executable was that triggered that eBPF program to run. So we can use that contextual information to do useful things. And with those useful things, we can change the way the kernel behaves. And it's really useful to be able to do this dynamically, because typically kernel releases take literally years to go from being created by the upstream Linux team to running in the production environments that you use every day. So typically, if you wanted to make a change to the kernel, you would have to persuade the whole kernel community, including Linus Torvalds, that it's a good idea. And it would have to be applicable to everywhere that uses Linux. And you would have to learn how to program in the Linux kernel. And then maybe you persuade everyone that this is a really great idea to make this change. But it still takes years for that change to actually make it to everybody's production environments. With eBPF, we can just write an eBPF program, load it into the kernel dynamically. We don't even need to reboot the machine, and we can create a change in that kernel. And it can be a bespoke change specific to what you need that day on that particular machine. We don't have to persuade the whole kernel community that this is a really good idea. So we get this ability to dynamically change the way the operating system is working. And importantly, we can do this without having to make any changes to the applications themselves. So an example I want to use to illustrate this is the idea that you get a network packet. We can look at the network packet and decide to do something with that network packet. In this example, I'm going to choose to drop packets. So I'm going to pretend that ping is malicious. Let's say every time we get a ping packet, I want to be able to drop those packets. So all I need to do is inspect each network packet, decide whether it is a ping packet, and if it is, then I'm going to drop it. So let's find this window. So let's find my code for that. So yeah, all we do is, there's a little bit more detail here. I can share the GitHub link if you're interested in how it parses the packet to decide whether it's a ping packet or not. And to start with, I'm actually going to send pass, which says just handle it as you would have done before. And over here, I'm just going to ping localhost. So the machine is going to ping itself. And we see every second it sends a new ping request. You can see the sequence number here ticking up by 1 every second. So let's just start by running the ping program. And, sorry, I've left this running over here. Keep forgetting that. Let's do that again. OK, so we're seeing a line of trace for every ping packet. We're not affecting the behavior yet. Now I'm going to change the program to drop the packet. And if I restart this, what we'll see is the sequence number over here has stopped going up, right? It's stuck at 42. We can see the trace is still generating lines of trace. We can see we're still getting ping packets, but they're no longer, the response is no longer being received here on the right-hand side. And then if I change it back to pass and rerun it, so update the eBPF program, we can see the sequence number. So we jumped from 42 to 71. So for about 30 seconds, we were dropping ping packets. So I was able to use eBPF to change the way that networking was behaving on that machine with a very simple eBPF program. I just want to turn a little bit to talking about how this is really powerful in a cloud-native environment like Kubernetes, or really any container environment. When we're running our applications in containers or in Kubernetes, they're running in containers inside pods, but however many pods we're running on a given virtual machine or a given machine, there is only one kernel. So typically in Kubernetes, that means there is one kernel per Kubernetes node. And every time our applications are doing anything interesting, like accessing the network or files, or whenever Kubernetes is creating new containers and new pods, the kernel is involved in all of those activities. So the kernel knows what's happening across all of our applications in all of our pods on that given Kubernetes node. And that means if we instrument the kernel on that node, we can be aware of and influence what's happening across that whole node, across all of the applications that are running in those pods. And we don't have to restart the pods. The life cycle of our eBPF programs is entirely separate from the life cycle of our applications running in pods. So we can use this for a whole generation of new and powerful infrastructure tools. For example, to create really efficient networking capabilities. In Kubernetes, we're running our applications in these pods, and we typically give each pod its own network namespace. And what that means is we've deliberately isolated networking in the pod from networking on the host machine itself. So if a packet wants to reach our application in the pod, in traditional networking, it comes in through the Ethernet port, it has to go through the whole networking stack on the host machine, then it goes through a virtual Ethernet connection into the pod, and it goes through essentially another copy of the networking stack in order to reach the application. Now with eBPF, in very much the same way that I was able to inspect packets and decide that it was a ping packet and decide to do something different with it, we can inspect these packets, figure out where they're going, realize this packet is destined for this particular application pod, so we can send it directly to the network namespace for that pod and avoid a lot of the overhead of running through the networking stack effectively twice. And that can lead to some really significant performance improvements. This is an example of a case study that we did with Trendyol, who are here in Turkey, and they saw some really great performance improvements moving to Cilium and eBPF-based networking. It's really the power of eBPF that's creating this kind of performance improvement. We can also, at the same time as we're deciding what to do with network packets, we can figure out that maybe they don't meet a network policy. So we can use eBPF to create network policy engines and drop packets if they don't meet certain security criteria. For example, we might say that one pod is allowed to access a given service, but another pod is not allowed to access that Kubernetes service. And we can drop packets if they don't meet those security policy criteria, using eBPF very efficiently. We can use eBPF to create some incredibly powerful observability tools too. One example is a CNCF project called Pixie, and this has lots of different eBPF-based sort of probes and programs that you can run in your Kubernetes cluster to get some incredibly powerful and sort of diverse measures of how your cluster is behaving. This example is a flame graph of CPU usage across a whole cluster. So it's used eBPF to gather CPU metrics across all the nodes and then aggregate them into one flame graph. Another example of observability would be the Hubble component of Cilium, which we can use to get insight into the networking behavior. So we can see individual network packets, we can see how those network packets build up into a service map, so which services are communicating with which other services. And we can also get metrics that tell us what's the latency, which services are performing well, are there some services that have outlier performance metrics that we need to investigate. So again, all of this is generated using eBPF programs that are observing these network events and using that to create this really powerful information that we can use if we're operating Kubernetes clusters. We can also use eBPF for security tooling. I've already talked a little bit about network policy as a security tool, but what about runtime security? We talked about how the kernel is involved for all these events that involve hardware, so things like accessing files and accessing memory and process starting and stopping and privilege escalation and checking permissions. And all of these things are interesting for security reasons. When we want to figure out whether something is malicious or not, it's usually going to be involving one of these kind of operations. So being able to instrument our kernel and instrument these kind of operations can be really interesting from a security perspective. So we use the term security observability to talk about observing these events and filtering out the ones that are interesting from a security perspective. And they're interesting if they don't match a policy or if they're outside a policy. So we might have a policy that says we want to know if certain sensitive files are accessed. Or we might have a policy that says we want to know if we're sending a network message to a suspicious-looking endpoint. So we compare the events against policy, and if they're outside of the policy, then they're malicious, and that's when we want to do something about it, tell the user about these events, maybe create some alarms or logs or metrics for understanding how often these events are taking place. So Falco is a CNCF project that uses kernel modules or eBPF probes to collect these kind of eBPF-based events, collect these security events, and then pass them to user space where we can compare them against a set of policy rules. And then based on those policy rules, we might generate alerts or generate some kind of activity that will kill the offending process. Another example of a security observability tool built using eBPF is AWS Guard Duty, which also uses eBPF running in Kubernetes as a daemon set. So if you're running it on EKS, it's running as this Guard Duty daemon set and creating alerts or creating events if it detects events that are outside the security policy. And both of these tools are collecting events using eBPF and then passing them to user space to compare against policy. One thing that we've done recently in Cilium with a project called Tetragon is the ability to filter those events inside the kernel. So we're making the decision about whether an event is potentially malicious or not, and whether we should tell the user about it inside the kernel, and only passing events to user space if they are deemed to be malicious, if they're outside the policy. So I want to show an example of Tetragon observing some security events. So by default, let me just start my log. So by default, Tetragon is going to tell us whenever a process starts and stops. This is really similar to the example I showed you in Hello World, where we saw every time a process starts. So if I've got a few pods running on this cluster, and if I exec into, let's say, the TIE Fighter pod, and I just run ls, we can see that generating events in Tetragon for the process starting and stopping. So it's going to do that for every process. And I've got some policies set up. I've got 2 tracing policies, I think. in this namespace. Yeah, so I'm monitoring for sensitive files, and I'm monitoring for network activity that's outside of the IP addresses that are in this cluster. So if I exec into the TIE Fighter and I curl to an external website, that's going to work. But we see, as well as seeing the process starting and stopping, we're also getting an additional event telling us that it made this connect request to an IP address that's outside the cluster. But if I were to curl to a local service like the Death Star, then we just get the process entry and exit logs here. We don't see an event about the TCP connect because it's not suspicious. It's not outside my policy. Another example could be if I look at a file that I think is suspicious. So the etc. shadow file has password information. So I want to know if people are looking at this file. And we can see we get read events generated for accessing that suspicious file. But if I looked at a different file that is not considered suspicious, then yeah, I just get the process entry and exit. What I'm showing here is just a very sort of compact view of the event information. If I just take out the compact for a moment, so we can see, a little bit, yeah, slightly weird. Okay. If I do the same thing with without formatting the output, we can see we're getting a ton of information here in this JSON output, including things like the container ID, the start time, user ID, labels of the pods. There's tons of information about this event, so we can understand not just what happened, but what pod it happened in, what service it happened in, what the executable was, what the user ID was. All this information is included in this JSON output from Tetragon events. So, yeah, right. So we're able to use eBPF here to get this very powerful information about security events. And because we're filtering those events inside the kernel, we see some incredibly low overhead here. So the actual amount of overhead depends on what it is you're observing. But for example, doing these benchmarks, we're doing 1,000 reads and then sleeping every nanosecond on 32 different threads. And we can see that by filtering in the kernel, we're getting a CPU usage of about 0.2% compared to over 3% for solutions that are doing the filtering in user space. So it's a really significant improvement, and I think a good example of how eBPF-based technology is still improving at a really significant rate. But what if we want to not just report on those events, we actually want to prevent them from happening? And this is something that we can do with Tetragon. We can, because we're filtering that event in the kernel, we understand from within the kernel, so synchronously to that kernel event happening, we can say, this event is suspicious and I want to stop it from happening. And I can do that synchronously. So what we're going to see here is not only is the event going to sort of log the suspicious event, but we're going to see it getting killed before it's actually able to take place. So if I find the right screen again, let me apply the network. No, that's not what I want to do. I need to edit the file first. So I'm going to just change this so that it will kill a request that's outside of policy. So any network request outside of the cluster. So I need to apply that file. Okay. So let's try, first of all, network request that we think is OK, because it's inside the cluster, and that would be a request to the Death Star API. Yeah. So we see the process starting and stopping, and that's what we expected. Now let's try making a request outside of the cluster. And what we see here is it got killed, and we didn't get any response back. Earlier, we actually got the response back from example.com. But by turning on that enforcement mode, we're able to prevent that request from actually ever being created, which is super powerful. OK, so I hope I've shown you how eBPF allows us to create these incredibly powerful tools that can improve the efficiency of networking. They can give us this incredibly deep observability insights into what's happening in our clusters. And we can build some incredibly powerful security tools based on eBPF. If you want to learn more about the history of eBPF, there's this incredibly high-quality documentary that was made about how it was developed right from the early days, how we persuaded the Linux kernel community that this was a good idea. I think it's really fun. So if you have like a spare half an hour, check out that documentary. And with that, I'll wrap up. I'll just remind you that there are going to be a few copies of Learning eBPF given away at the end of the day. And I don't know, do we have time for any questions? Or
Is it? Yeah. We have time for 1 or 2 questions if there's any. OK, I'm taking it to Burak.
My question is about the capabilities of the eBPF in the application level tracing. Okay. Let's assume that we have a superpowers in the network visibility for eBPF. And my question is there any eBPF helper for parsing HTTP packets in the actual C code which is running in our eBPF virtual machine? Okay. Do we have any HTTP helpers for parsing, getting requests, response headers, and bodies? Is there any feature like this?
So the questions are asking about helper functions, and just to sort of explain, helper functions are functions you can call from inside your eBPF program to, well, get help. They're kind of kernel functions that you are allowed to call from within eBPF. And so, for example, things like getting the current process ID or getting the, actually even accessing memory, you'd use a helper function to do that. So the specific question is whether or not there's a helper function for parsing network packets. There is not. But you can do it. I mean, you have to do it by, in much the same way that my code there was inspecting a packet to look for the header that says whether or not it's a ping packet or not. You can do that kind of parsing. We do have in-kernel parsing of HTTP packets in the proprietary isovalent version of Cilium. So, you know, there's no easy kind of here's the code, here's how to parse it, but it is possible to do with eBPF. Okay.
One last question. Okay.
First of all, hello, and
Hi.
welcome to Istanbul.
Thank you.
So I have a question about seccomp, like system calling states between eBPF or Cilium. What are the differences between like your product and Docker, like seccom's differences? Are they?
Sorry, can you hold the mic a bit?
Okay.
I can't hear you very well.
Like, what are the differences between like seccomp and eBPF?
Okay, the difference between seccomp and eBPF. So seccomp is a, I guess, kernel facility that allows you to have rules about system calls. So it is actually implemented using BPF, the kind of precursor to, I think it's BPF rather than eBPF, but it's the sort of precursor technology. And what you can do with seccomp is make some pretty binary rules around like this application is allowed to call this set of system calls, but not these other ones. It's hard to configure, partly because as application developers, we usually don't really know what system calls we're making. And also because it's very binary. It's kind of, you can either read files or you can't read files. Whereas with eBPF, we can be much more kind of bespoke about this. We can write a more sophisticated program that is not just saying what's the system call, but it can also be looking at what's the path. Maybe it's a different, certain user IDs are allowed to do this activity, but not others. We can have much more sophisticated policies if we do that with eBPF. And then if we look at something like Tetragon, rather than having to write sort of the detailed eBPF code, we can write a YAML format policy, which is still potentially going to be non-trivial to write, but it's much easier than writing the eBPF code that can sort of articulate these rules that might say you're allowed to read a file, but with a more dynamic approach to what those rules are, what the kind of criteria are that we're going to allow or not. Does that help?
Yeah, for sure. Thank you very much.
Welcome.
Thanks, Liz.
Thank you.
All the way here. Please accept this.
Oh, thank you very much. Thank you. Do you want to do a photo?
They want to take a photo.
Okay. Ooh.
Thanks a lot for being here for a week now. Like she was in Kubernetes Community Days first, and she's now here, so we are lucky to have you in Turkey.